This is Chem 112, Unit 4, the second half of Part 1, and this is on nuclear chemistry. Nuclear reactions take place in the nucleus of the atom, and they're significantly different from the ordinary chemical reactions that we've studied throughout first and second semester Gen Chem. We're not so interested in the electrons anymore. So before we dive too far into this, there are four fundamental forces that are in the universe that are known to science currently. The first is the gravitational force. This is the weakest, but certainly acts over by far the longest distances. So this is what keeps the planets in orbit. This is what keeps us on the ground. This is what's responsible for gravity and weight, etc. The second is the electrostatic force. This is a much stronger and shorter distance force. It acts at a much shorter distance than the gravitational force. It's also much stronger, and this is basically what explains most of chemistry outside this chapter. You might remember from previous chemistry, Coulomb's law is the law that sort of models the electrostatic attraction or repulsion. If we have same charges, two electrons near each other, those will repel. And we know from, again, previous chemistry that energy is transferred as a result of electrons changing energy levels, and that exists as photons or packets of light. Going even smaller and stronger, we get what's called the weak nuclear force. This is the force that's responsible for certain types of nuclear decay, like beta decay. We'll learn more about this as we go through the chapter. And then we get the strong nuclear force. This is the strongest force that actually binds protons and neutrons together in the nucleus. It is much stronger than electrostatic force, and it explains how protons are pushed so tightly together, despite all of the charges being the same. So yes, there's a significant amount of electrostatic repulsion inside a nucleus, but it is dwarfed by the strong nuclear force that binds them together. As we sort of get into this a little bit, it's going to be important to sort of understand the differences between what we're studying in this chapter and what you've seen prior. So again, chemical reactions, these involve electrons shared or transferred between atoms. In regular chemical reactions. Now, nuclear reactions, electrons are going to be moved around as well, but we're not interested in that because the energy associated with those electrons moving around is essentially zero in comparison to the changes in the strong and weak nuclear force that we're going to see, and the amounts of energy that these reactions are going to release. A couple of electrons being transferred around to keep the charges neutral. Yeah, that's definitely happening in the background, but we don't care. Atomic mass and mass numbers in regular chemical reactions don't change. In nuclear reactions, they do. In nuclear reactions, we are going to be interested in specific isotopes. Certain isotopes are going to undergo certain nuclear reactions, whereas other isotopes won't. And so we're going to be looking specifically at specific mass numbers and things as we go through this. Regular chemical reactions obey the law of conservation of mass and the first law of thermodynamics, which gets into the law of conservation of energy. In nuclear reactions, the sum of the mass and energy is conserved, but they are not conserved independently of each other. Mass and energy can be interconverted, which again we'll get into as this chapter goes along. And as we've seen in the previous chapter, our reaction rates are affected by a lot of different variables, temperature, concentration, catalysts, etc. Whereas in nuclear reactions, the rates are going to be dependent only on how many nuclei we have. So a little bit of review from first semester general chemistry for those that remember this stuff. If you remember this, great. If you don't, here's your chance to brush up on it. The word nucleon. Nucleons are protons and neutrons. This is the particles that exist in the nucleus, as opposed to electrons, which are not nucleons. They exist outside the nucleus. And so we describe an atom by looking at the number of protons and neutrons in the nucleus. Remember that the atomic number, Z, is the number of protons. That's the atomic number on the periodic table. The mass number is the total number of nucleons in a nucleus. So it's the sum of the protons and the neutrons. And so you might remember this nuclide notation where we put the mass number in the upper left corner. We optionally can put the atomic number in the lower left corner. It can or cannot be there. It doesn't make any difference. And when we have atoms of the same element that have different numbers of neutrons, different mass numbers, we get isotopes. There are 3 common names for the isotopes of hydrogen that you should be familiar with in this chapter, particularly this middle one, deuterium. That's an important one. Protium, deuterium, and tritium stand for hydrogen 1, 2, and 3, respectively. So if we were to write that in nuclide notation, we would have this notation here. The nucleus is most stable when the neutrons and protons are in certain numbers and ratios. And so when we say that a nucleus is stable, we actually mean that it's not going to undergo much nuclear chemistry. What we observe for stable isotopes is that for small elements, and again, giving you a guideline for small, we're basically talking about the first 20 or so elements on the periodic table. Those are going to be the most stable when the ratio of neutrons to protons is approximately 1 to 1. As you get to heavier elements, that neutron to proton ratio starts to increase and starts to approach 1.5 to 1. The largest stable isotope known to science is bismuth-209. And bismuth is atomic number 83, so what that means is that all elements with atomic numbers 84 and higher are automatically radioactive. They are in some way unstable. There are 2 other elements in the 1 through 83 range that are also completely unstable, and those are Tc and Pm, elements 43 and 61. So basically there are 81 different elements that have stable isotopes. The other thing we tend to notice as we look at the patterns of stability here is that even atomic numbers tend to have more stable isotopes than odd. That's not a hard and fast rule. There are some exceptions. There are a couple of even-numbered ones that don't have many stable isotopes at all, and there are a couple of odd-numbered isotopes that have several stable isotopes. But for the most part, even numbers in general tend to have more stable. So you can see a table here of all the known stable isotopes in the universe. If you add all those up, and I haven't done that, but if you add all those up, 147 plus 53 plus 48 plus 5, there are 200, I think I punched the button wrong, 48 plus 5, yeah, 253 known stable isotopes. Again, out of 83 elements. So on average, divide that, that's about 3 stable isotopes per element that has a stable isotope. And obviously there's a range there. There are a few stable elements that only have 1 isotope. There are a few stable elements that have 6 or 7 different isotopes that are all stable. But there are 253 total spread out over 81 different atomic numbers because, again, 43 and 61 don't have any stable isotopes. And notice the numbers there. When both the protons and the neutrons are both even, that's over half of our stable isotopes, 147. Even numbers of protons, but an odd number of neutrons, that accounts for 53. Odd even accounts for 48. And there are only 5 known stable isotopes that have both an odd number of protons and an odd number of neutrons, which is sort of an interesting thing. So again, that serves as a bit of an introduction to this chapter. The next segment of the video will go into nuclear binding energy, the idea that this strong nuclear force that holds the protons together, and we can actually calculate that as it turns out.